nanohub.org.
Online simulation and more for nanotechnology.
So good morning, everyone. My name is Gerhard Klimeck. I welcome you to the recitation session number 2 on semiconductor device education. I'd like to start out with the NanoHub homepage, so nanohub.org. We're really having 4 major agendas in mind when we created NanoHub. We wanted to have people being able to model and simulate, use real research codes, but make them usable to others. We want to enable people to learn and teach, to develop software, and then also share and publish their results, their new tools, their lectures, their tutorials, etc. With a resurgence and interest in semiconductors, there's also a large effort now in the US to develop workforce around semiconductor devices. So we have a new landing page here right from the NanoHub. If you click on workforce education, you will go to a landing page that keeps evolving. Last week it looked slightly different, same content though. So what we have here on this landing page is really geared towards the teaching of semiconductor devices and teaching new engineers and staff members that might operate facilities to teach them about devices and processes and circuit modeling. So there's really a couple of major headlines. What I'm going to highlight today and demo today is the immersive learning through simulations. But we also have open courseware, a variety of courses are hosted on NanoHub that are immediately relevant to this topic, ranging from fundamentals of transistors, device fundamentals, thermal engineering, advanced transport, so a variety of topics. There's in some of those cases, there's free textbooks associated with it. And then we have, of course, more tools that are apps that are relatively easy to use. And then we have tools that really require expertise. We're partnering with commercial vendors now. MATLAB and Thermocalc and ABACUS software is coming soon. And then we have partners and we have ongoing faculty engagement. And there we have this recitation series that we ran starting last December and in January. So the first incarnation is here. You can find the results here, or you can also navigate to these groups from the buttons up here. So let me dive into the semiconductor device fundamentals, which I really like to demo today. And what we have assembled there is a tool set that really aggregates a variety of tools together that are otherwise scattered on NanoHub. And they really deal with crystal structure, band structure models, bulk semiconductors, PN junctions, bipolar junction transistors, MOS capacitors, and MOSFETs. So here are the animations of these tools, and each of these topics have their own headings, so to speak, and you can navigate to them. And we'll be looking at PN junctions today. And I'm going to launch, if I click here on PN Junction Lab in ABACUS, I go to the ABACUS tool page, or the app page. And so the app is a publication. So it has a DOI. It has been cited. It's been used by some 17,000 users. There's authors. And there's a variety of materials that go with it. You can look up the citations. There's some questions. There's some reviews. There's also wishes where people request additional material into the tool set. And we try to act on those. And then you can click this Launch Tool button here, and it will launch this tool. It'll take a couple of seconds. Here is our ABACUS tool. You can always resize a tool a little bit here so it fits better into your given screen. Do that. And so these are the tools we have in ABACUS, and they start, as I said, from crystals and band structure, going to semiconductor transport in bulk, and then PN junctions, then there's BJTs, MOS capacitors, and MOSFETs. So let me go into this PN Junction Lab here, which is our traditional, one of the very early tools in NanoHub that we have. And there, it pops up here in this tab, or you can also select these tools from the drop-down here. One of the tabs has some homework assignments associated with it directly in the tool that you can download. You make this a little bit bigger still. And to me, I think what's really still cool is this tool under the hood runs a real industrial strength tool called Padre. So this Padre came from Bell Labs, and it did design real transistors. This is not a toy application under the hood, but a real, honest-to-goodness simulation engine. So if I go in and just hit simulate, what I get is a PN junction here that has a slightly asymmetric doping that was specified. It has an asymmetric length of the P side and the N side. And I get the conduction band edge, the valence band edge, and the Fermi level. I can also select outputs here, and I can look at the energy band diagram as a function of bias. So now I can ramp through the bias, and as I increase the bias in a positive direction, you see how the barrier gets smaller and current will flow. And if you have a very high bias, you also see this band edge dropping down, and that's really resistive drop that you will never find in a real textbook, displayed graphically in this form. And that actually came up in my class last week, where students were working on a homework assignment, and they looked at these band edges, and then they noticed that there's suddenly a drop here in the potential, and they came back in the recitation, and we discussed this resistive drop. Obviously, here is the IV characteristic that is also being calculated. What's also interesting, at least for teaching and for the concept, is really to look at the net charge density in this device. So here is this PN junction, and you see really the depletion region of carriers here. And as I increase the bias, the forward bias, you can see the depletion region decreasing, and it no longer is really a square type approximation. You can really see how non-flat, so to speak, non-square this distribution is. So you can do a couple of things right off the bat here. One is if you wanted to explore different doping levels and explore what how Fermi levels really change when you have a different doping. So I'm increasing the P doping to be, let's do it not so high, low through the scales. So here now you can see how the structure is looking quite different. I can compare actually the previous simulation to the current one. So here is what you see in deep blue is the heavy doping calculation with 2E17. And if I click down here, I can compare that to the previous one with 2E15. And you really see how asymmetric the structure gets, how strong or how flat the bands here are. This means there must be a very strong electric field in the device as we have this high doping. So why don't we look at the electric field? And let me turn this off a little bit. So you really see that on the low doping side, the electric field drops over a significant spatial region, versus on the heavy doping side, the field is extremely strong. And if I compare that to the previous simulation, you saw it was quite smooth. And there's the analytical approximation is also plotted in here. And if I now look at my net charge density. In the original case, we had the beautiful depletion region approximation that looks quite visible here. Now, everything is quite crunched up because you have this extremely high doping. Let's go back to the band edge diagram and the band edge diagram as a function of bias. And you can really see how the how strong really the electric field here is being flat here in the conduction and in the valence band. If I go back to more modest dopings again, I'm going to make the structure to E15, make this also 2E15. And I'm just going to move the structure to be symmetric. Clear this out and run this again. So I'm making the structure symmetric. Now the junction is in the middle. Things look rather symmetric too now. If I go to the net charge density, this looks very nicely symmetric, almost square. I can look at the total. At zero bias, there is noise. So here you see the hole density. This is actually the hole current in the electron current that is being resolved, and it rises up. And what I wanted to look at here is really the hole density, and here's the electron density. And you can see how as you increase the bias, the charges flood into the depletion region, and electrons are making it over to the p side, and those are the minority carriers that then carry the current there, and then they collapse at the ohmic boundary condition here at the end. So you can look at the charge distributions internally to the device, and these are the doping lines, which are just step functions in this case. So here we can look at excess charge carriers. These are the differential charge carriers that are sitting at the junction, and you have the electrons here and the holes here. So you can really look into the internal distributions of carriers in such a nominally simple device, but you can really dive into it. All right. In this band edge diagram here, also on the high bias, you see the drop. It's also so this is the resistive drop. It's also kind of interesting to then explore with students what these quasi-Fermi levels mean and how they drop across the device and mimic the minority carrier distributions in this structure. And this tool, as I said, is reasonably sophisticated. It has really designed transistors. You can change a variety of things in it. You can change the temperature and the bias, but you can also, in this case, also change the minority carrier lifetimes. So if you, for example, make the lifetimes very short, so let's make it really short. For argument's sake, we should see some consequences on the quasi-Fermi levels and on the minority carriers that are penetrating into the device. And here, this actually now ran the Padre simulator. So this is an example I had not run. Previously, it just pulled out the results that other people had run before. So if I now go in my band edge diagram here, I should see that minority carriers really don't make it deep into the device. And you also see the resistive drop being enhanced in this device. And you should see that then also in the IV characteristic here, where you get two significantly differently looking IV characteristics in the device. And you can track that down then to the minority carriers, etc. So these are interesting exercises to go through to understand the relationship between minority carriers, etc., and their lifetimes, and then the IV characteristics. I also want to, so here, maybe before I go into reverse bias, let me just do this comparison again. So here is the band edge diagram with the Fermi level, quasi-Fermi levels dropping rather rapidly around the junction and not reaching out far as before, close to the contact. So in this case, when the minority carrier lifetimes are relatively long, the minority carriers, the electrons on this side, holes on that side, really still diffuse throughout this 3 micron long device and eventually get destroyed here at the ohmic contacts. Versus if you are in the case of really short carrier lifetimes, the minority carriers really barely make it across the device, and then they vanish. So quite different, and you can see the results in the IV as well as the band edge diagram, and you see it in the resistive loss here. You can also run this IV in reverse. So let me do that. So you just reverse the voltage. And it's now running the simulation from 0 volt into the negative 0.6 volt. And now as I apply a voltage in reverse bias, you can clearly see how the barriers is getting bigger. I still had this really fast relaxation time, so you can really see how the quasi-Fermi levels are for the electrons and the holes are hugging the intrinsic level. I had in my class where I'm teaching with the PR textbook, there is an example of a homework assignment where these quasi-Fermi levels actually reach into these bulk sections, and we use this tool to explain that really can't happen. And you can go in, for example, here, go in the materials and make these much longer. Let's make them quite long and compare how the quasi-Fermi levels look like. And if that's the case and they survive a long time, you should see a significant difference in the quasi-Fermi level, and the reverse current should not be a whole lot affected. But so let me go in here, energy band diaring at applied bias, and now you can see how the quasi-Fermi levels are basically beginning to hug the valence band edge and the conduction band edge, but they will never cross. So in some textbooks, you might find that this line is actually crossing in, at least as a conceptual exercise. And that, at least for my students, caused quite some confusion. And then having a visualization like this, where you begin to understand how quasi-Fermi levels depend on minority carrier lifetimes, etc., in reverse bias and in forward bias, that's quite powerful to immerse students into a variety of questions. And the IV characteristics here are in reverse, and I don't think there's much to be seen between these two different simulations. We're not running this into breakdown or anything too wild. So, I mean, this is roughly what I wanted to show with the tool as a first start. So I focused today on this PN Junction Lab. Let me focus, my thought was this issue we had has been resolved. So here is a more modern looking version of the same tool where you can launch it out of ABACUS here by just clicking on PN Junction Lab, or when you're on the splash screen, click on, where are we, this guy, PN Junction Lab, and you will get another window in which you have this more modern looking tool. It actually under the hood runs the same engine, PN Junction Lab, and in fact it connects to the older style tool and runs it in the background and retrieves the information, but it shows up automatically with results. Same results here as what I had shown. Here you can see we have plotted in also the analytical expression for the depletion region. So same results, more modern look and feel, and we're working on converting many of our apps that we have that are popular into this more modern view. So there were some persons that look at photovoltaics. There are resources on NanoHub that deal with photovoltaics. Let me So if you go into model and simulate, here on the photonics, I believe. So we have a variety of photonics tools, also some tools that deal with PN junctions and photovoltaics more directly. The best way to find that is NanoHub. It's, I think, PV Hub, Nano. PV Hub. Yep. So there's a big group page for photovoltaics on NanoHub, and there's a variety of tools available. So we can put that in the chat for people to use. Chat. And then I heard one mention of material science. There is a slew of materials on materials. So if you're really teaching, you can go to this Teach and Learn and look at materials where we have curated educational resources. There's also a tool set for materials. Let me pop up this one. And here was also the photovoltaics piece. So there is materials courses that you can pull in. And that also includes, we have now work on machine learning for material science. So you might find these resources useful. And use the similar areas. Okay, so here's the simulation-powered curriculum where we have tools assembled that teach, or you can use in the class to teach. So these are all tools that deal with different structures, etc. There was another one on process modeling, I believe, or so that's also available on NanoHub. So if you go here, semiconductor workforce development, you click on this semiconductor processing and devices. There's a tool set similar to ABACUS, but it's focused on TCAD more in general. So there's process modeling, there is some PN junction modeling, and there's also circuit modeling, all in one place as well. So process modeling, there is some simple oxidation apps that run a process modeling tool under the hood, and you can look at the different oxidation rates and diffusion rates through oxides. And then there is a device simulation component which deals with drift diffusion and PN junctions of what I just demoed, a bipolar junction transistor. And then some circuit simulation, which is really a simple version of SPICE. So that, I think, were some of the addressing some of the teachings that were listed. Maybe I didn't capture them all, but if you have questions, I'll be happy to answer questions as well.
The first question, which are the length range to consider long or short channel?
So that's more a transistor question. And I am doing that in my grad class as a project, and we're going to host a recitation session on how to do this in NanoHub with a variety of tools. So we have a couple of tools that you can use in this regard, and I have to really pull together like a one-stop shop for doing so. So right now I would have to so I would pull in this tool here, which is a multi-gate FET, where you can look at short channel effects and reduce the effects of, well, you can scale the gate down. You can actually also, come to think of it, let me go back to my, oh, by the way, all the stuff that I ran, if you're like lost and you had sessions up and running, you can go to your dashboard and it'll show the sessions that you have been running, and they expire after about 3 days. So you can stage certain things and then go back to them. So here's this tool I was using. If I were on a different browser, that's fine. You can also share these tools. And here in this MOSFET lab, you can go in and begin to scale down this transistor to shorter gate lengths. So you can, if you run 100 nanometers here, it should actually pull out a cached result. And you can reduce it down to, say, 60 nanometers. And if you really want to get into short channels, you actually have to change the body size, etc. And that'll be part of a recitation session in 2 or 3 weeks. So I'll go into more details then. So you can do simple downscaling of a standard MOSFET here in ABACUS. And if you really want to go to nanowires and multi-gate FETs, that's a bit more advanced than what I let students do that in projects. But I'll cover that in a couple of weeks.
All right, the next question, can this simulate two-dimensional PN junctions such as graphene PN junction?
This tool, no. The app, no. The tool, I don't think can be coerced into graphene simulation. We have a couple of graphene simulators on NanoHub. I am not sure if they do PN junctions per se. They do like FET-like structures or band edges, etc. For infinite graphene. There is a new 2D FET tool which has, say, modern 2D materials, TMDs, etc. as an option. I don't know if graphene is one of those options, but it's a bit more of a researchy thing, I think.
All right, the next question is, can we simulate solar cell?
Yes, to a certain degree. It's not in this ABACUS tool, and there is a tool called Adept 2.1. It's the latest one. All right. So here's a more graphical user interface where you can specify layers, etc., and specify different absorption files for gallium arsenide and materials, etc. So this is a more sophisticated tool, but it is here. So Adept 2.1. And this should be on the photovoltaics page, because that is from the same group of people that really run the photonics program. Photovoltaic program.
All right, the next question is the transport drift diffusion for PN junction or corrections.
So this is straightforward drift diffusion. You can make the simulation engine do more complicated things, but for that you have to go into the full-fledged tool. So let me. So here, if you go into the output log, you can see this is actually the input that goes in. It's a reasonably complex input. And if you speak Padre, the language under the hood, you can modify this to your heart's delight. So the way you go about this is you launch this Padre tool, and here are a variety of input decks, including a PN junction, and that is close to what I had demoed. And here you can choose additional models that are included in corrections. And to really choose them, you have to go into the manual, etc. So this is the full-fledged Padre tool set, and you can certainly address more complicated models in them. In the PN Junction Lab, we have not turned them on. Any other questions?
Oh, we did have one more question come in. Okay, this was related to the previous question. They said that they meant conjugate gradient correction.
I'm not familiar with that correction, but I can point you to the Padre manual, and we can all right, so here you can in your preconditioner, you can choose conjugate gradients. That's what I'm familiar with as a numerical method, and you can address those as options for acceleration. All right. Any other questions?
I think one more question just came in. Can we use the PN model with QW's simulation?
With, sorry, QW?
QW's?
Quantum wells, maybe?
Quantum wells.
Yeah, this tool does not have quantum wells in it. We have a couple of tools that have quantum wells. Where you can design a variety of heterostructures like these, for example. So you can look at a HEMT type device, etc., and look at quantum wells like this, or like this, or like this. So maybe that is one way to address the need. And you can, it's like a design window where you can put in reasonably arbitrary layers, etc. I thank you very much for your attention, and I'll hope to see you next week. Thank you very much.